In this lesson, we're going to look at double integrals over general regions. Let's examine this three-dimensional space. Imagine that we have a point on our x-axis, and we'll call this A and this B. So x equals A and x equals B. And we'll draw the line. Here's the line. X equals A. And here is the line x equals B. Now imagine we have two functions of x such that y is a function of x, and one of them looks like maybe parabolic. So here we have this function, y is a function of x. So y1 is a function of x. And then we have another function of x that looks like this. And this is our y2, which is also a function of x, but a different function. So this is function 2 of x, and this is function 1 of x. Now we have another function of x and y that gives us a height, where we say that z is some function of both x and y. Z is our height, and the height depends on our x and y value. So at a certain value of x and y, we achieve a height, z. So let's throw some heights in here. There's another height. Maybe we have a height here. And then we have a height here. Maybe it's a small height. And let's give a height here. Let's see, the height here only goes to this point, and a height here that goes to this point, and sort of connect them. This is our surface. So what we have is a top, and we have a three-dimensional volume. We have our surface here. This is the surface of our volume, which is here. And it's the top of it. And then we have sides, and I can make the sides a different color. Say this is the front face here. And then we can give it a side face in blue here. This is our side face in blue. All right, let's move this up, and let's think about what we have here. What we want to do is we want to look at a surface area. Let's look at this red surface or face that I've got right here. This is a sort of a slice, okay, and this, we'll call this A. This is some area A. And we could have multiple slices of A if we were to slice this. Here's another slice A. We could have another slice, and this is if we sliced slices through this volume. And these slices are parallel to the YZ plane. Now the area for each one of these slices is the area with respect to x. So depending on where we are in the x-axis, we'll have a different slice of area, and we would integrate this from y sub 1, or f of 1 to f of 2. So y sub 1 to y sub 2. You could say y equals f of 1. So from f of 1, f sub 1 of x to f sub 2 of x. And our integrand, in fact, is the function z, or f of xy. And our variable of integration is y. So this gives us the area for each slice as we sort of slice through this volume. And what we want to do is add up all these areas from A to B. So if we want to find out, that is to find the volume. To find the volume, we are going to integrate from x equals A to x equals B. Each one of our slices, we're going to add up the area of each slice, and our variable of integration is dx. So if we put this all together, let's see if I can move this up a little bit more, give ourselves some room. When we put this all together, the volume is equal to a double integral, where the outer integral, we go from A to B, of the area, which is the integral from f sub 1 to f sub 2 of f of xy, and the variable of integration for the inside integral is y, and the variable of integration for the outside variable is x. So this is the double integral that gives us the volume of our solid under a region, above a region. Let's work an example. Here we're going to find the volume of the prism whose base is the triangle in the xy plane bounded by the x-axis and the line y equals x and x equals 1, and whose top lies in the plane z equals f of xy. So let's draw a diagram. We'll start with the line x equals 1. So here's our line, our x-axis, x equals 1. Now let's draw the line in the xy plane, which is y is equal to x. Imagine this is in our xy plane, and this is a line y is equal to x. And if we moved over in the xy plane like this, we would have x, when x is 1, y is 1. Now let's create a table to find our height, z, at different values of x and y. Let's find out for 0, 0. When x is 0 and y is 0, if we plug that in for f of xy, we get 3. So when x is 0 and y is 0, z has a height of 3. 1, 2, 3. So z has a height of 3. When x is 1 and y is 1, z has a height of 3 minus 1 minus 1, which is 1. So at that point, we would move up, and z has a height of 1. And then when x is 1 and y is 0, z has a height of 2. So we're going to go up 1, 2 at the point 1, 0. So here are the points on the corners of our triangular base, how high they go, and if we connect them, we're going to get the top of our solid. So now we need to find the volume, and let's see if we can manage moving this up. There we go. Now what we want to do now is we want to find the volume of this solid figure. And so let's start it with a double integration. The volume is going to be the following. We are going to integrate from 0 to 1 along the x-axis. Oops, that's 0 to 1, not x. And then we're going to integrate from 0 to x along the y-axis, and then our integrand will be our z, f of xy, which is 3 minus x minus y, and our inner variable of integration is y, and our outer variable of integration is x. So let's work out the first integral, because we need that to get the integrand for the outer integral. And so here's our outer integral from 0 to 1. And the antiderivative of 3 minus x minus y with the variable of integration of y is 3y minus xy minus y squared over 2. And that's going to be evaluated from y equals 0 to x. This is going to give us our integrand for the inner integral, and there's our variable of integration, which is dx. Now, when we do this, we're going to take this antiderivative and plug it in x. And then if we take this, subtract from that the antiderivative with a plugged in 0. Well, if we plug in a 0, each one of these terms is gone. So the solution to this integral is merely this antiderivative with the y is replaced with x. So this says that we're going to find the outer integral from 0 to 1, and our integrand for the outer integral will be 3 times, not y, but 3x, minus x times y, and y is equal to x, so x squared, minus x squared over 2. And then we've got a dx. Now what we want to do here is let's combine like terms, because our last two terms in the integrand are like. So we have 3x minus, and we've got an x squared and a 1/2 x squared, and they're both negative, so it's a negative 1/2 or 3/2 x squared. That's our integrand. And then we have our variable of integration. So let's find the antiderivative with respect to x. That's going to be 3x squared over 2 minus 3x cubed over 2 times 3, and we're going to cancel out the 3's. Boom, boom, like that. And that's evaluated from x equals 0 to 1. So when we evaluate this, we're going to evaluate it between 1 and 0. So if we put a 1 in, we end up with 3/2 minus 1/2. And of course, if we evaluate it at a 0, we subtract the integrand with a 0 in it, and that goes away. So it's 3/2 minus 1/2, which is 1. So our solutions, put a box around it, to the answer is 1 unit cubed. Let's work another example here. We're going to calculate the double integral where R is the region that is a triangle in the xy plane bounded by the x-axis, the line y equals x, and the line x equals 1. And here is our height. This is our z value, z of f of x, y. So our region in the xy plane, here's our y-axis and here's our x-axis. Let's make it look like an axis here. There's the x-axis and y. And we're looking, this is sort of that's a y, our bird's eye view here. So there's a y-axis. And when we draw this, we're going to have the line y equals x. This is the identity function. Y is equal to x. And then we're going to have the line, the constant function, x equals 1. So this is at the base of our solid, looking down at sort of a bird's eye view. And so, let's see, let's move this over here and let's work out what this integral would be. Well, this is going to be equal to, and I think what I'll do is write it down here. We're going to integrate from 0 to 1, or that's our outer integral. Our inner integral is going to go from 0 to x. And our height function is the sine of x over x. And the inner variable of integration is dy. We sort of put a bracket around here because this integration is going to give us, we have a dx on the end. Let's move that over here. Okay, so when we look at this, we can see that when we evaluate y from x to 0, it's going to be x minus 0, which is x, which means that this is equal to x, and it's in the numerator, and it cancels out with this x. So we end up with the integral from 0 to 1 of the sine of x, and of course the x in the denominator is gone, dx, and the antiderivative of the sine of x is the negative cosine of x, and that is evaluated from 0 to 1. So that's equal to a negative cosine of 1 minus a negative cosine of 0, which is basically a negative cosine of 1 plus 1, which is approximately equal to a 0.46. So here's our solution, and this is units cubed. And that gives us the volume. Now we're going to look at finding limits of integration. When faced with evaluating the double integral, we integrate first with respect to y and then with respect to x, and we take the following steps. Sketch the region of integration and label the bounding curves. Next, find the y limits of integration. Finally, find the x limits of integration. Here we have a diagram of a region. It is the region enclosed by the circle x squared plus y squared equals 1 and the line x plus y equals 1 in the first quadrant. Imagine drawing a line parallel to the y-axis in the direction of increasing values of y. And we want to start by looking at where we first enter the region, what is the value of y, and when we exit the region, what is the value of y. Well, when we enter the region, y is equal to 1 minus x. That could be our, say, y1. And when we exit the region, our y2 is equal to the square root of 1 minus x squared. Our last step is to find the x limits of integration. Well, if we start at x equals 0 and work our way over to x equals 1 and continue to draw these lines or slices parallel to the y-axis, we can see, to go through this region, that we would integrate from 0 to 1. So for our x values, our first x value for integration, our limit is x is 0, and our second value, x of 2, our final x value, is x is 1. So our integral becomes, the inner integral says that y is going to go from 1 minus x to y is equal to the square root of 1 minus x squared. And our outer integral is going to go from x is equal to 0 to 1. And we are going to integrate the height of our solid at every xy point in our base. And our first integration is going to be with respect to y, and our second integration is going to be with respect to x. Of course, so we do the inner integral first. Variable of integration initially is y, and then the outer integral where the variable of integration is x. Let's try this example. So what we want to do is we want to start by drawing our region. Here we have y is equal to x squared. That is our lower bound. And y equals 2x is our direct variation, which is our upper bound. And it gives us the region right here. So let's move this up to here. And let's look at this in a different perspective. We're going to swap our integrals. So we're going to actually have our first integral have a variable of integration of x. And the best way to do this is to graph this again. So let's graph this again. But we're going to look at it from a different perspective. We're going to look at x as a function of y instead of y as a function of x. When we do this, we see that we have x is equal to the square root of y. And then our other graph, when we have it as x is a function of y, we get x is equal to 1/2 y. So now in this case our slices are going to go horizontally like this. And when we do this, our double integral is going to go from 0 to 4 on the y-axis, and then from x equals y over 2 to x equals the square root of y. And our function, 4x plus 2, is integrated first with respect to x and second with respect to y. Let's look at properties of double integrals. The first rule is the constant multiple rule, which says that if you have a double integral over a region and your function of x and y has a constant multiplier c in there, you can factor out that c as follows. You can pull that c right out front, factor it out, and then you can evaluate your integral over the region for the integrand f of x, y. Let's move that up here. If I can squeeze that, see if I can squeeze that over a little bit, move that there, and get that on one line. There we go. Our next rule is the sum and difference rule, and that is if we have a double integral over a region of the sum or difference of two functions, so we have f of x, y, and then we have g of x, y, and we add or subtract them and integrate over that region, that's actually equal to the sum or difference of the individual integrals. So the integral of f of x, y over a region plus or minus the integral of g of x, y, that's a double integral, over that region. Our next rule is the domination rule, and it says that if we have a double integral over a region of our function f of x, y, and it's greater than or equal to 0, this is true if and only if f of x, y is greater than or equal to 0 on the region R. That's the first part of the domination, let's put that there. And the second part is that if we have the integral over a region of f of x, y, dA, and that's greater than or equal to the integral over a region of g of g of xy over the area. This is true only if f of xy is greater than or equal to g of xy on the region R. Our last rule is the additivity rule, which says if you have a double integral over a region of f of xy, it's equal to the integral, the double integral over a region, and that is of region 1 of f of xy plus the double integral over region 2 of f of xy if R is the union of two overlapping regions. So let's move that up. So if R is the union of two non-overlapping, so this is, let's put a non in there, of two non-overlapping regions, and those non-overlapping regions are R1 and R2.